Next speaker is Mike Wolf, and he will continue with his lecture series on asymptotics of high energy harmonic maps from Riemann surfaces.
Okay, well, thanks to, I was telling Charles, I can't really see who's come back, but thanks to those of you who have, and apologies to those who didn't. So I want today to speak about some more recent topics and more global ones. In some sense, we've been talking about maps from C to, so let me back this up. So previously, we've been talking about maps from C to some space X, some symmetric space. And I'm in some sense, this is, I imagine this is being local, and I'll explain what I mean by that. And now I want to talk about maps from a surface with some structure on it. Not quite sure how to indicate the structure sigma. It's a letter I haven't used. Also to X. And in some sense, everything will be equivariant. So I'll be really talking about, this is S tilde, where S is a differentiable surface of, say, genus G, and it makes most sense when G is at least 2. Okay. And in this case, what I'm thinking of X is what I said last time. I indicated we're really interested in this symmetric space SL3R mod SO3. It's kind of a baby version of some stuff that you may hear later about from Parker and perhaps others. Okay, so let me summarize quickly where I want to go in the first few minutes, and then I'll back up a little bit. So everything is based off of this parameterization by Laborie and Lofton. This is independent, and I forgot to look up the when. Lofton's PhD is about 2000, and Laborie was both before and after that, in some sense. They proved the same theorem. And what they're looking at is, say, the moduli of convex RP2 structures on S. So we had said last time, I'd quickly given you this description of you have RP2, and last time, we had some polygons in RP2, for example. We didn't have to. I mean, we also could talk just about in RP2 some just basic convex shapes, trying to draw a convex shape that's not a round circle or an ellipse. So, and then over that, there was some affine sphere, parameterized from by some projection from down below. And over here, we have some other affine sphere that I can't draw very well, where the edges, where it is asymptotic to something which has a straight edge. And, I'll recall, and so when I have such a situation, say in this latter case, and I have I'm not sure, some group action, taking me from some fundamental domain to some other fundamental domain, say by some element G, that is almost certainly invisible to you. I hope that's a little better. Then I have a minimal surface. I'm sorry, then I have an affine sphere, which has this invariance under G, and the resulting minimal surface to this symmetric space also has that invariance. So So Riemann often parameterizes the space of convex RP2 structures. I suppose I should, put in some equivalence. So up to some sort of structure preserving map in a homotopy class. And they're studying this, and what they show is that M may be represented by pairs of a Riemann surface and a cubic differential. So, so here, this is a Riemann surface, and this C is a holomorphic cubic differential in, let's see what I want to say. KR cubed is a way of saying it. So, so this is the same sort of cubic holomorphic differential. C is C of Z dz cubed they talked about last time. And I think I'm writing smaller than I did before, and I think that was problematic. So I'll try to write bigger now. So they're saying that, so the picture that we have going on here that they are representing and is that this moduli space of of RP2 structures or some other sort of equivalent to other things we talked about, minimal surfaces, I'm just not going to write it, is can be parameterized this way. We have the parameter space of Riemann surfaces, type Moore space, and then on every one of these Riemann surfaces over this, we have this a fiber creating a bundle over this type Moore space, and the fibers are these vector spaces of holomorphic cubic differentials. So really, we have this bundle of the whole moduli space gets depicted as a bundle of holomorphic cubic differentials over type Moore space. Okay. Maybe I untangle things a little bit. Well, so I'll just sort of repeat. I have a Riemann surface here. I have a pair here, RC, and looking at this point. So what does this point represent? This point represents a convex RP2 structure on S. And their theorem is saying that every convex RP2 structure on S, everything that you might represent in this way with some group action on the structure. So maybe I'll try to draw it bigger. So I have this structure and acting on this, and this is meant to be, well, and so there's a map from the universal cover into RP2, which means that there is some action on this space by a representation of pi 1 of S into the automorphisms of RP2. And that action, so if I have some element of pi 1 of S gamma, then rho of gamma is an automorphism of RP2, and it takes regions in RP2 to regions in RP2. And if you like, it takes there's a fundamental domain for this action in RP2. I don't know how to draw that. And this representation is moving it around inside this image of the universal cover. So it's your standard picture of a group acting on the universal cover. It's just here the representation is into RP2. And all such actions, all such images of the universal cover into RP2 yielding some convex domain equipped with some action of the fundamental group of the surface, all of those such objects are represented by a unique point in this bundle. And the proof goes through looking at, I'm going to tangle this up, looking at these affine spheres. Okay. So, and then this is, of course, what I said last time, this is such an object is equivalent to a minimal map. I don't know how. Some minimal map. Oops, don't want to use that. V from the universal cover of R into this symmetric space. Again, where this is acted upon by a representation of the fundamental group into aught of X, which in this case will be SL3R, I guess. SL3R. Okay, great. So that's the picture. And right. And as I said last time, just to recapture a little bit of this, how does this point define this? Well, everything goes through this, so this parameterization of structures goes through the equation that we wrote last time, this wonderful equation with these wonderful signs that makes some of the people in the audience either jealous or disgusted by how easy it all is. This Ouyang equation, which I call W. In this case, I'm going to have, this is all happening on, so this equation, and I would say on the R, so, which is S with some other structure, say G, a symmetric. And so we do pick up a sort of curvature term here, and that's what the KG is. For example, just put a hyperbolic metric on the surface that's conformal to R, and then you'll pick up its curvature here. And then once you know, and we showed last time, that once you know R, and so that's a domain for C, and you know U, then you have enough to write down those frame equations, use the frame to develop this affine sphere over the domain in RP2, and that affine sphere the frame field is integrable to give you the affine sphere exactly because this is the equation for integrability once you know C is holomorphic. Then once you have the affine sphere, that's enough by this other construction to get you a minimal surface. Okay, so I am talking about minimal surfaces, so I'm not entirely disqualified from this conference. Okay, what do I want to do? I guess I'll pause here briefly to see if there's any confusions I can quickly clear up. I'm sort of determined not to run too far over on this lecture, but I'm always worried. So I'll pause. Okay, I hear no objections. I think I can still hear everybody. People are there, right? Somebody's there. Host is there. You guys can hear me?
Question? No.
Okay,
Okay. Yeah. You can continue.
I'll continue. Okay, great. So what I want to talk about today with all this setting is I'm interested, I am interested in compactifying M. So now for compactification, I need to know the asymptotics, say in this parametrizing bundle of C over C of S, maybe, over the Teichmüller space of S. So I'm not going to be able to achieve this. And with full disclosure, I'm becoming increasingly suspicious of the program I'm going to suggest as to whether it'll work. But I can say something, so who knows? Oh, I should say that this also, since I related it to minimal surfaces in the symmetric space, this is also the parameterization of, maybe I'll say, hit 3 of S. So this is the Hitchin component of representations of pi1 of S into X, for example, into SL3. Okay, these are discrete faithful representations and a distinguished component of that representation space. The one studied by Hitchin in a beautiful and landmark paper in 1992. Okay. And so really the goal is to have some compactification of this Hitchin component in some sense along the lines of the, of the Thurston compactification of hit 2. Okay, but I started to say that. So let me redraw the picture and tell you what I'm going to do the very first, most basic example of this sort of asymptotics. So redrawing this image, I have Teichmüller space. Here I have C of S here. I have some Riemann surface. And now what I'll do is I'll pick out a particular C0, some cubic differential. And so that cubic differential, I'm running out of dimensions here. I can create a ray of cubic differentials SC0. And what we've just said, because this is a parameterization of this moduli space associated to S, this family SC0 or H1, there is some representation rho S of pi1 of the surface into SL3R. Or if you, so, and maybe I'll abuse notation, also into aught RP2. So I have some family of representations into my moduli space of geometric structures, and I am, and my question is, what can I say about the limits of this as S goes to infinity? That's the question of the day. Describe the asymptotics. And we're going to use the ingredients that we've developed in the first two lectures. And, you know, when in the last lecture, what was the ultimate part of the last lecture was that we had these polygons. We had, for example, z to the k dz cubed has a cubic differential. It had some sort of singular structure, which I drew like this, and then various sectors corresponded to triangles in here. And when we had a different sector, that was a different triangle. And there was and we developed from the frame equations a particular unipotent U taking me from green to pink, just leave it like that, unipotent that was happening far out in the sector going from here to here. This is going to play a role, and so I'll come to it in a minute. 10. Okay, I'm going to try to quickly do some foreshadowing. I had in the first lecture also talked about maps to harmonic maps to H2. What happens in the analog for harmonic maps to H2? So let me pause here. The question of the day, before I launch into that, the question of the day is this. I have a distinguished ray in this moduli space that is giving me a family of representations. And I'm curious, what can I say about the asymptotics of this family of representations? If you like, this collection of, and so what does this do? This this representation, it will take a element of pi 1 of S, and it will associate to that element some matrix in SL3R, and actually a family of matrices, one for each S. And what I'm asking is, given the data of a particular cubic differential, then if I look at a loop, element of pi 1 of S, and we know associated to that loop is some matrix, what's the asymptotics of that matrix? This is a matrix that has 9 entries in SL3R, and somehow I'm hoping that I can say something intelligent about the asymptotics of this matrix. It's likely going to have entries that grow with S. But maybe after normalization, I take out the high term of an S. It's going to grow actually like S to the third. I divide by S to the third, and I'll get some sort of limiting object, I hope. And maybe that goes back to this local, something about C0 is going to be evident in that. That's the hope. Okay, let me pause there and see if there are questions about the setup and the dream. Because otherwise the rest of the lecture is lost if you don't know, if somehow I've lost people as to what it is that I hope to display.
Okay, so you can move it. No question. No question.
Can you say that? I didn't quite hear that.
There are no questions.
No questions. Okay, great. So I have to speed up and make some questions. Okay, so let's take a chance and say, go back 40 years and say, you know, so what happens in hit 2? So this is the family. So this is the moduli space of equivariant harmonic maps from R tilde to H2. The way it's set up, there is one fixed Riemann surface R, and I've written it badly, so that's a Riemann surface R, into H2. And you recall that, so what does that mean? So this is in just the plain old Teichmüller space. Oh, sorry. So equivariant harmonic maps H2, or and this is supposed to be equivalent to Teichmüller space. And so the picture here is I have R naught, and in R naught I have a tensor space, the space of quadratic differentials. And in that space, I have a Q, and I can extend Q to array SQ, and then I have associated to that array some family of representations rho S. So these are now hyperbolic metrics, and I am asking, what is the asymptotics of those hyperbolic metrics? What are the asymptotics of rho S, this representation from pi 1 of S into hot H2 PSL 2R? And it is all supposed to involve ultimately these harmonic maps. So since it involves the harmonic maps, everything is going through the equation, Laplacian, that we talked about last time, this Bachner equation. Laplacian H2 is 2e to the H, Laplacian HT, 2e to the HT minus 2e to the minus 2h minus HT q squared, and then plus some curvature. So it's all going through that, and I want to know what happens to these hyperbolic metrics. And to know that, I have to know what happens to this element, rho S of gamma. And I can think about this as an
I think there is a question.
as an isometry of H2. Yeah, what's the question?
Yeah, there is a question. Yeah.
So Mike, it's Rob. I just want to interpret for me and for everybody just the picture. So the point where that green tangent vector is R naught, the spaces you're looking at, the blue space looks like a tangent or maybe cotangent space.
It's a vector space of so it's a vector space of quadratic differentials.
But to interpret the picture, am I supposed to be thinking of that as like tangent space of the black?
I'm being suggestive and just as it being a sort of permitting an exponential map or defining an exponential map. So you know, to a ray in the vector space, I get a family in the space.
Yeah, but it's a family of conformal structures of Riemann surfaces.
Hyperbolic structures.
Okay. Fine.
I've written it as a family of representations because I really want to be thinking that way. But it's, I mean, the representations are equivalent to a family of hyperbolic structures.
That's fine. I just wanted, it's for me and everybody to interpret that picture. Thank you.
Yeah, I'm going kind of fast. I'm apologize. So, it's one of those things. Well, I'll probably go so fast where everything I'll say I will correct and it will just wash over people. So I appreciate the question. So, maybe I'll just draw a picture of what's going on. Um, you know, I have this Riemann surface R naught and it's high genus. And it has this quadratic differential on it, which I've drawn in, I don't know, I think I have the colors for this. And so, that has some divisor. And we talked about, there's a nice picture of what this divisor might look like. It has zeros of different orders and okay. And now, and this was Q. And so what happens in SQ? Okay, well, it's the same basic picture. SQ has the same zeros, the same order of zeros in the same places in some sense as Q, but everything gets scaled. So if you focus on a particular point, for example, maybe you focus on this point here. Oops, I don't want that color because it's a non-zero point. So if I focus on this point, what happens? Well, under rescaling, what you see is the zeros retreat, and all you really see is the complex plane in this point. Or you focus on this zero, and what do you see under rescaling? Well, I hope this works. All you see is in the limit. So, and maybe I'll just try writing this. How did that happen? So as S goes to infinity, this neighborhood U with SQ, we can think of that normalized as converging to C with just this quadratic differential C squared dz squared. And that was what we studied in the first lecture. We know what these maps look like, right? So what are these maps from C to dz squared? For this particular one, this has image of an ideal quadrilateral. So using that, I can do this. It's one of the advantages here of being in a being a Zoom talk. I can do that rescaling. I hope that was visible. I hope that was visible. So what is going on here? And now I'll be very well. Okay. So in order to understand this representation, let's, I have, let me redraw the picture. I have this surface S, and, I have some, how do I imagine gamma? So how do I imagine gamma in pi 1 of S? Well, there's some curve. Okay, so I don't know, maybe it goes like this. And I can represent that curve as doing maybe something like this. So, I don't know, maybe it goes to here, here, and then makes its way back. Well, in the image, remember that, and so my point is through here, I'm thinking about a harmonic map, from so in this region, get a color. In this region, I have, as I blow up, so this is asymptotic to C to H2, with Q having no zeros, just dz squared. So in here, the map is a projection. And this was a projection. Over in here, I have a map from C to H2, where Q was z squared dz squared. I think this is probably invisible. And the image map, as we drew last time, is like this. So if I put the entire thing together, what my picture looks like as in the asymptotics is that this neighborhood develops to some ideal triangle. In between, the green part is just a projection. The pink part develops, this is a little tricky to draw. Oops, yeah, maybe this. Into some ideal quadrilateral. This other part over here is light green. It's going to develop. So in between, again, everything is just projections to geodesics. So the stuff in between is this stuff in between is just some sort of geodesic, but these things are linked together in a by the topology of the surface and the projection, so that let's see, what color should I use here? Light green. And up here I'll have some ideal pentagon. So what happens to this curve gamma? Well, maybe it comes in here, and then it's going to ride along the edge of this ideal polygon, maybe make its way through. I guess it goes to the other side, ride along that edge, make its way through, etc. And that's what the rho s of gamma looks like. And what is interesting in terms of hyperbolic geometry is its length. Well, now be really fast. This is as you make your way across an ideal polygon, that's some bounded length. But what really matters is these connections, and they can be very, very long. And so they will be something like s to the half times some sort of characteristic number. And what is that number? It would be, because of the way the projections work, and all be in terms of the horizontal foliation, what we end up with is that the length of gamma is like s to the half times how much this curve gamma intersects this horizontal foliation of Q. That's really fast. I'll do this more slowly in the, now I'll do it slightly more slowly and with more development in the case of SL3. But what the point is that but the point is this: I can predict the holonomy, the asymptotic holonomy, by looking at ultimately the defining holomorphic differential and its local form. Well, I'm sorry, I defined by the holomorphic differential. So quantities associated with the holomorphic differential predict the holonomy. This is global. This is somehow I'm using local information to do this prediction. So more global stuff washes out at infinity. And the way the proof works is that harmonic maps for these structures localize. So I don't have to worry about, where this curve goes and how it goes in this representation. I just need to worry about the neighborhoods it visits. And I understand every neighborhood and I understand how they're patched together. So I understand exactly the limiting geometry of the curve. Okay. All right. I'm not going to pause for questions on that because I'm going to sort of redo it. Okay, so now I'm in the setting of SL3R. And our picture again is I have Teichmuller space. I have this bundle of cubic differentials. I have a particular Riemann surface. I have a C0 and I have a ray, SC0. And associated to that, to SC0, there is some representation, rho S, of the fundamental group of the surface into SL3R. And I want to know the asymptotics. I want to know what goes, as much of the geometry of rho S as I can. I'm probably not going to know much about rho S in here because it's because it's a global problem. But maybe as I go up to infinity, enough localizes that I can understand it. Okay. So let me try to get to a statement of what I would like to prove. Okay. So there's two numbers. There's two ways of measuring, there are two measurements associated to this ray SC0. The first is I have rho S and this representation. Thinking of as matrices, maybe I'll just say formally I have the holonomy of this. So I'm looking at the matrices. And I can take some sort of norm. I don't care what, some sort of just multiplicative norm. Okay, and that's a number. And I'll just say that you can work out in a number of ways that this, whatever this number is, it grows like S to the third. So maybe I'm interested in the holonomy rho S. Maybe you take a particular gamma, and then you divide by S to the third, and I want to know what that is once I normalize. And so that's going to be something finite, and that's going to depend somehow on gamma. It's going to depend on gamma, on S, and ultimately on the defining C0. Okay, that's one number I can pick. There's another number I can pick. That it depends on CZ, that it goes, and it's just entirely in terms of this cubic differential C0. So I'll start with C0, which is some cubic differential C0 dz cubed. And there are 3 cube roots of C0. say alpha 1, alpha 2, alpha 3. So in other words, alpha I cubed is C0. And these will differ, of course, by roots of unity. Now, let me do a little more geometry. C0 is holomorphic as a tensor. So, and C0 is C0 dz cubed. So if I look at the absolute value of C0, that's some funny tensor, but I could take the cube root of it, and that will define some line element, ds, say ds C0. And what do I know about that line element? Well, away from the zeros, it's flat. If you compute the curvature of this, so how would I do that? I would do Laplacian log of C0, and then I'd do something. But C0 is holomorphic, so log of the absolute value of C0 is harmonic. So this is 0. So the point is that this is a flat metric, and everything I said was away from the zeros. So what happens at the zeros? It has cone angles of size 2 pi plus pi over 3 times k. To 2 pi over 3 times k at order k0. Many people in the audience know if I'm right or wrong, and about the 2 and about this formula, and I do appreciate their silence. Okay, so some formula like this, but I mean more. You have an excess cone angle. So your picture looks like this. So I have a Riemann surface. Again, I have some zeros. And if I have a curve gamma, I can think of the curve gamma. So think of gamma. Or represent, better to say it this way. Represent as a geodesic. And so as a geodesic, it's where I have flat metric. So it's going to go, I mean, maybe it just avoids everything altogether. It could be over here. So this might be gamma 1. But another gamma, oops, I don't want to call it gamma 1. That's a mistake. Here it is. There's a delta. Then gamma will make its way across the surface, and it's likely, because of the high cone angles, going to be required to visit some of them, and it will just make its way around the surface as a geodesic. And as a geodesic in a flat Euclidean metric, it is a straight line between these zeros in that metric. And so I'll have these components, say gamma 1, gamma 2, gamma 3. This is back to gamma 1, that this geodesic decomposes into, which have initial and terminal points as arcs on at these zeros. And that's just this is a non-positively curved, is a flat singular space with cone angles more than 2 pi. This uniquely represents the curve gamma. There is just one such geodesic. So there is, this decomposition is unique. So, okay. So,
Quick question. So this is like a la Teichmuller using the length of the shortest geodesic in this flat metric to represent the holonomy in the SL3 case. That's sort of like,
at this point, I haven't said anything about holonomy. At this point, I am just representing the curve class, the free homotopy class of gamma as a unique curve on the surface. In this case, a C0 geodesic.
okay.
So I'm writing gamma uniquely as gamma is. I probably have to do it. I don't know which way I'm going. Gamma 1, gamma 2, gamma 3 by concatenating them. Now, in terms of C0, there is also, in some sense, a holonomy. So, and what I'll point out is along gamma J, we can find period I'll say period I of gamma J, by which I mean I take one of these cube roots, say alpha I, and then I figure out how much, well, what is the integral of that holomorphic one form over this uniquely defined arc gamma J. And so that's a period of gamma J. I have three of them. They differ by cube roots of unity, but I have these periods. And this is all in terms of the geometry of C0. And then I will define the intersection number of gamma with C0 in some funny way. I'll start with the period of gamma J with respect to I. That's a complex number. These are holomorphic forms, alpha I. So I'll take the real part, and for each gamma J, I have three of these. I'll take the biggest one. So it's the maximum period among the three choices, differing by roots of unity, and then real part. And then I'll add up over all the gamma J's. So we traverse, what's going on? I take gamma, I decompose it this way. For each one of these segments, I look at the cube roots of C0. Those are some one forms. I will get some periods, and I will just, and I'm interested in, well, and I'll take the real parts. That's why not? I need some real number, and I'll just add them up, and I'll pick up the biggest ones. So here I might be using alpha 1. Here I might be using alpha 3. Okay, it is what it is. Okay, so that's some number. Okay. And I'll point out, maybe we just modify this formula a little bit, that if I put in S here, I mean, that's not visible, then here comes out an S to the third. Okay, so this is also going to grow like S to the third with SC0. Okay. So now I have two numbers. So let me write down, so we have two numbers. On the one hand, for each gamma, I have the holonomy of this matrix, rho S of gamma, and that grows like S to the third, so I can pull that out. And I have this other number, which is this intersection number of gamma with SC0. That has nothing to do with the representation. That only has to do with the parameter. And you know, the S also grows. Everything here grows like S to the third. So, well, I guess I can divide by S to the third, and guess really I'm looking at gamma against C0, and I'll just remind you what this is. This is the sum over all these J's, all these pieces, gamma J, and I take the period of gamma J using one of the each of the forms. I take the real part, and then I take the max, okay, over I, and then I add it up. So the biggest periods you can get on the subsegments added up. I have these two numbers, and the theorem is that if I take the limit of the holonomy of rho s of gamma, properly normalized, as s goes to infinity, I'm looking at asymptotics, what do I get? I get that asymptotic holonomy is exactly predicted by this this intersection number, or if you like, this sum of maximums of periods. So that's the theorem that my co-authors proved and put my name on. So this is Lofton, Tamborelli, and me. Okay. And how does this, okay, so I should say some remarks. Oh, shoot, I was going to finish early. Drat. May I have a few minutes?
Yes, yes.
Okay. So one remark, and you know, in talks are kind of boring to hear what other people have done. It's much more interesting to hear like what they can't do and what you can go think about. It's been remarked that this formula has a tropical flavor, right? So in the sense of like, oh, you know, tropicalizations, tropical geometry, you know, the where we do algebra where you know, we have some notion of plus, and how do you think of plus? You know, it acts as max, and how do you think of times in your ring operations? Those are really plus. So you can see this sort of tropicalization here, where you know, we started with a product of periods, a product of gamma j's, and that becomes a plus, and the sums of the periods become some sort of max. That's very imprecise, and I don't. There's something tropical about this. We're doing asymptotics. Maybe we expect something tropical, but I don't really. Well, I definitely can't articulate some conjecture as to how to make things properly tropical or why it's true. Just it's intriguing to me. The theorem is strange in two ways. So strange. The first is we were just adding up maxima. Why are we adding up maxima? Why is that the right thing to do? The other thing is that it ignores, you notice in this, I've been emphasizing for hours now that the critical part of all of these conserved quantities of the holomorphic differentials are the divisors. So this ignores the divisors apparently of C0. I mean, they're sort of there because they allow you to break up gamma, but they're not figuring in the formula. What's figuring in the formula is what's happening to gamma outside the zeros. Not much what's happening to gamma inside the zeros. So what is going on there? So let me just tell you why this is true. Very quickly, in my remaining -3 minutes, here's what's going on. It is the same picture as in the H2 case. I have some zeros, and they have this sort of sector decomposition. And we've already talked about how we have these gammas, being broken up into geodesics. Okay, well, now through here, remember that we had talked about, we have F inverse DF, and this was some matrices DZ and some matrices DZ bar, and what was involved here was the U and the C. It's tremendously schematic, and the U and the C were related by, and these are related by this Ouyang equation, which we analyzed. Well, in this region, so maybe I'll give it a name. I'll get some picture. In this, U0 region, we'll have C will be a constant, and this little u will be a constant. And it's actually, and so I know, so the, F inverse df is constant. I bet this is illegible, but all this, and this is a work of John Lofton by himself, it says that the holonomy is relatively easy to work out. So you get the holonomy of rho s is like this intersection number of, I'm going to try to write this in better language. So what this says is that, this is by Lofton, that the holonomy in rho s of gamma I is very easily worked out to be this max of the period gamma j. Okay, of gamma j, max of the period sub I. Because you know everything about the affine sphere or the minimal surface, and it's all, when you go to infinity, it's all trivializes. As we have said, it's all, I started off this series of lectures by talking about the most trivial harmonic map in H2 being a projection, and this is the SL3 analog of a projection. So you can work everything out. Okay, so then what goes on here? Well, I am, for example, coming in on this arc, I'm going to use alpha 2. And on this arc, for the maximum, I'm going to use alpha 3. And they each have well, and they, I over here, I do have an alpha 3, but its eigenvalues in the real part are smaller. So how do these get mixed? How do these get put together? How do we understand the holonomy? Well, I'm going to modify things. I am not going to use, shoot, I was worried about that. Instead of using these particular arcs that I've drawn here, the geodesic, I'm going to make a shortcut. I'm going to come around like this. So my new arc will come here, it'll go here, it'll go there. And remember that to get from here to here, there is some particular unipotent, UK plus 1, from the kth sector to the k plus first sector. And that unipotent will say whatever holonomy you've gotten coming in like this, well, now apply the holonomy to get to this sector. Apply the unipotent to get to this sector for the holonomy. Then apply the next unipotent, then apply the next unipotent, then apply the next unipotent, and then you can keep going. So actually, I know that the holonomy of gamma is given by, the holonomy, I'll just, blah, blah, blah. The holonomy of gamma 8 followed by a bunch of different unipotents. I don't know, good notation, from 7 to 8. And then, the holonomy of gamma 7. I'm trying to be suggestive here about writing a formula. You have the holonomy coming in, then you have a bunch of unipotents and the holonomy going out. And my collaborators very, very carefully worked out that these matrices are complicated enough that they will transport the high value of holonomy here, that high value that high value here of the holonomy will be preserved under these unipotents to be multiplied to the high value of the holonomy here in the matrix. So in the end, the largest term of this very complicated product of matrices is determined by the holonomy of the pieces. Okay, too long. I stop. Thank you very much for attending and for the interest and for the questions and the patience.
Okay, there is a question from Rob.
Always, yeah. Hey, so first of all, much applause. Second, two questions related to just the last remarks. On the independence of the divisor, does that suggest that you could, instead of looking at this special case where you've got zeros of high order, you could look at just simple zeros and do the calculation somehow there? And that's one question.
Okay. Well, this cubic differential has the zeros it has, right? So it may not have simple zeros. It may just have zeros of order 11.
Sure, sure.
And so on that ray, you're stuck working out the holonomy on that ray. It's approximated probably by some cubic differential with simple zeros. Now you're taking another limit, right? If you want to approximate the cubic differential and also do the asymptotics, now you have to think about what happens as you go out, a family of approximating rays. How do they converge to the limiting ray? Good luck.
So the second question is related. Okay, so Zenheit. So I mean, the parameter S, I don't know whether you want to take S to the 1/3, but if you try to, so you're taking the limit as S goes to infinity. If I use another parameter, sigma, that's like S to the -1/3, say, or excuse me, I don't know what the right parameter is to take, but is there an asymptotic expansion, like the next terms in this one over S or 1 over S to the 1/3 or whatever, that
I mean, what are the errors?
Maybe reveal something about the first question.
Oh, okay. So there's okay. So I was there's a bit of theater in what I say. Hey, there's no contribution. There's no apparent contribution from the zeros. Well, there's no apparent contribution from the zeros in the formula. There, of course, there is a contribution of the zeros because they're telling you which gamma, how the decomposition of gamma J, the unipotents that carry you from one to the other are there. Okay, so I should confess that, you know, I was just trying to set up a passage in my talk. So yeah, it should. I mean, I don't know how much. I don't want to make a statement beyond that. You don't see anything in the formula that involves the zeros because they definitely are important. The higher order terms, yeah. So the higher order terms are people try to study. This would go in some sense under this, I think, whether in this sort of WKB approximation type theorems that are somewhat popular, or WKB analysis of what the next terms would be. I don't think I should. I think I'm way over my skis just saying that. But
Even in the in the SL2R cases, there's, I mean, that's stuff you did 40 years ago, but in the SL2R case, in the Hitchin 2 case, is there something that's interesting? I just was trying to get some flavor for the asymptotics. Yeah. Is there something interesting?
I know some things about that. Yeah, I mean, there is some interesting things. I mean, you do well, of course, you saw in the last lecture, maybe, you know, the error terms showing up, this Bessel terms, which, of course, then give the unipotents. So in some sense, you can see, you see aspects of the zeros showing up there because you use these particular unipotents. And people, I don't have a statement to say there, particularly right now. I'm a little tired, but I don't have a good statement just to offer you. People do try to study all the orders of the asymptotics. This is some of this work by Berger, Iozzi, Pozzetti, Perot, on this real spectrum compactification. In some sense, as to the limited extent I understand things, they're trying to capture all orders of the of S in some compactification. It's a pretty big compactification to do that, but they have some positive claims.
Okay, thanks.
There is one more question.
Hello. Yes. So I was just wondering about the parameter. This rho s, you took those s's over the complex, or is it real?
Oh, I chose S to be real. I'm sorry.
But I was actually wondering, maybe my question is a little imprecise, but morning Professor Franz gave a talk where he was talking about using the one parameter, he was constructing the matrix d lambda for the Yang-Mills equation. So I was wondering, is there any connection to the asymptotics you see from the representation? You are trying to get some metric. Is there any connection in the limiting case? So he actually quoted a theorem of probably Ulembeck, where he was mentioning about harmonic maps construct flat connections. So he had a one parameter family of metrics. So I was trying to see if there is any relation via the representations which you did today.
I would expect so. But, you know, you have Franz right there, and I'm sure he can just hold forth on this very precisely.
Yeah, sure. Because I was just wondering, you did one parameter representation.
Yeah. No, it's a perfectly fair question. It's perfectly reasonable.
Because he mentioned like characterize using d lambda is flat for every lambda. So you are somewhere looking at the asymptotic. So like, is it anywhere in the limit you are trying to get some flatness? You are mentioning in one where you were having a picture where you are, as you go larger, you are going like C, like Z d square. You had an example where like that you mentioned.
Yeah, I think you're right. And I know that I can't say something precise right now, so I'm sorry. I think but I think actually, I really do think Franz can give a clear answer. Yeah, I don't think I can hold forth on this in a coherent way at the moment. I'm sorry. If I were there and I went to think for a little while, maybe I could, but I can't do it on the spot right now. I'm sorry.
Yes, thank you very much.
But Franz can.
Hey, Mike. So I had a question about if there's some way, some generalizations to this, maybe to other rank 2 groups, because it seems like maybe it doesn't matter so much that it's a cubic differential.
There's some stuff to some extent. Gee, if only I had a student who like were working in that area. Okay, so there is something I buried that sort of comes out. You know, I just had norm. I could have taken the highest eigenvalue. I can still say something about, say, the largest eigenvalue by the same method. But I'm going to use a trick, which is there are in SL3, these are 3 by 3 matrices, and there are 3 eigenvalues. Right. The product is 1. So I really only need to know 2 pieces of information. But the highest eigenvalue that I would find for the holonomial of gamma is going to be the lowest eigenvalue of the holonomial I find for gamma inverse. And in doing this asymptotics, I get to use both gamma and gamma inverse. So in some sense, I can locate all of the eigenvalues of gamma if you allow me to use the information about gamma inverse and its highest one, or its norm. Okay, well, suppose I'm in, I don't know, G2 prime. Now I have a lot more eigenvalues, and I can't play the same trick, at least directly. Maybe something about the high norm, yeah. And of course, in G2 prime, I think I'd have to check with an expert, but I think I have less information about the unipotents. Is that right?
I think that's right.
So it, SP4, I think I have enough information about the unipotents. I might run up against this issue of needing 4 eigenvalues. And so in some sense, I need 3 pieces of information, but I only have 2.
Hi, Mike. Hello?
But that's a good aspiration.
Hi, Mike. Hi. Oh, okay. So I have a question. So do I really have to go, do you guys really have to go along rays? I mean, if I kind of sneak up on a ray
okay, so
continuous, right? I mean, you still get this formula.
Right. Okay, so a few comments. First of all, this is a talk, not a paper, right? So there's some cheating going on. I was a little bit careful when I drew stuff You notice here, I went like down the middle of a sector in every time. I was like, okay, so, we'll use the unipotent from this sector to this one to this one. It's possible that my gammas would come in along like the wall of a vial chamber is really what's going on. Or I come along, no, maybe along a better way, say a Stokes ray or an anti-Stokes ray. And then, then what do? I have to worry about that sort of edge case. And so in the paper, there's a couple of pages about that and and you sort of do it by approximations. But you're absolutely right that if, instead of using that gamma, I used something like this. Well, I'm doing periods of holomorphic forms, and so Cauchy's theorem will tell you get the same answer.
No, sorry. I think you misunderstood. Oh, by ray, I mean
Yeah,
the ray
clearly.
in the vector space of cubic differential. So if I sneak.
Oh,
I think there's.
yeah, you're right.
Continuity there.
Completely misunderstood. I think this is really subtle.
Okay.
I think this is part of the problem with extending this is that it is, so as I understand your question, so let me reinterpret your question. I have this cubic differential bundle, and I have, I talked about this ray. I don't think this is quite your question, but I can let it be. It's a version maybe. I have R naught that I started, or R and R prime, and this has some limit, and I can imagine maybe I have RS or RT. Let's make this RT, and let's make it a little easier to see.
Right.
So I have RT heading in like this, and I can just have some path, which is RT CT or SCT. That's badly written. Make it bigger. So I have something like this.
Yes.
And you can ask, what's the asymptotics in this? And maybe T depends on S.
Mhm.
Now what's the asymptotics in S as I move the Riemann surface in, as I go out here? How does that depend on this T of S, for example, and this CT of S? It's not obvious that you can interchange limits in easy ways, that all different sorts of asymptotics, even if my RT was, even if the Riemann surface were just fixed and I'm wandering inside this vector space of differentials, I don't know that we get asymptotics that are independent of the path.
I see. Right. I guess my original question was, I mean, it seems like you're saying something about unit norm cubic differentials, and I was wondering if there's continuity there, right? Because,
Oh, yeah, I mean,
yours is a more complicated situation, which you drew out here, but mine was a fixed Riemann surface.
I mean, if I did, S times 5C0, then the asymptotics will be the same because I'm really comparing two sides of things that I will,
No, that I agree. Of course, if you scale C naught by 5, then of course it's the same. But I was saying if I have, you look at a sequence of rays, right? Like C.
Yeah. So you wanted something like
convergence of rays, exactly, for the fixed Riemann surface.
So you wanted something like SCS.
Maybe a different. I guess we can use the same letter for. Yeah, that's fine. Yeah.
Well, you're going to have a family of cubic differentials parameterized by S.
Right.
And then you're going to go out them at some rate.
Yeah, that's fine. That's fine.
Yeah. And I don't think I know And I don't know that this is independent, that you get identical limits. I don't think I know that. I'm not sure. I certainly don't know it at the moment.
Okay, yeah.
I'm a little worried that I am trampling on the host who wants to let people go to dinner, but I'll just say that.
Yeah, I think if there's additional questions, people can always email Mike, if that's okay. Okay, I'll return it back to.
So thanks the speaker for this wonderful talk.
Thanks, Mike. Good to see you.
Thank you so much.